Okay, thank you all very much for having me. It's been exciting to be here. I've been excited to meet and talk to people. Because there are so many new faces for me in the crowd, people I hadn't met before, I actually decided to broaden the talk a little bit from laser experiments and also just talk about some more broad laboratory experiments on magnetic reconnection that go into some other experiments that I and collaborators have been involved with. So I thought it could help stimulate discussion and potential avenues and collaborations and things like that. Okay, so yeah, overall punchline of my talk is that I think laboratory experiments are very exciting and they provide some valuable complementary data to what we can get from spacecraft and astrophysics observations. Pretty much I'm just going to give you a tour through reconnection experiment results. First I'll show our lab reconnection experiments, the MRX and VTF, meter scale, what I call discharge plasmas. In those experiments, we've studied fast reconnection through two fluid effects. These are plasmas that the whole system size is close to the ion skin depth or ion gyro radius scale. So the two fluid effects are very apparent, and we can study that. It's important in the magnetosphere. So we've learned a lot about two fluid effects. We've also studied particle energization by reconnection and seen lots of the associated waves that are driven in the plasma during the reconnection events. And then I'll get into laser-driven experiments, which are a new frontier. The big difference I see is that in the laser experiments, you can get to a much larger system size compared to an MRX or a VTF, and then potentially also experiments in relativistic regimes. And I'll show experiments with current sheets, instabilities, and particle acceleration. So I'd like to just quickly thank all of the collaborators. These are all very collaborative experiments, including the group at MRX, that's at Princeton, and then experiments at the NIF and Omega EP. Even during the pandemic, we were doing experiments. In that case, it was all over Zoom and everything like that. So we have our obligatory Zoom screenshot. So I think in this day and age, the simulations are so good. Why do we even need experiments anymore? I ask myself that question a lot. But I think that lab experiments give us a ground truth, a demonstration of a phenomenon. The laboratory in particular can provide us repeatable and controlled conditions for doing these experiments over and over again. We can get very detailed 2D and 3D measurements in comparison to a spacecraft which may just have a few spacecraft through these complex plasma environments. So we can verify and test our fundamental plasma behavior in models and even discover new and unexpected behavior. The laser experiments in particular also leverage an enormous investment in laser facilities that's been built up from the laser fusion program in the last decades. So they can get us to really interesting plasma conditions, and there's high quality plasma diagnostics. They can give us images of different quantities in the plasma, going from global scales down to the kinetic scales. And we're always improving how we analyze this type of data, so getting more and more information from it. Okay, so first I'll talk about what I call discharge plasma experiments. So this is the MRX experiment at PPPL, and it's now been upgraded to a new version that's about twice as large geometrically and about 10 times as much energy, called FLARE. There's another experiment called the VTF, which I worked on when I was a graduate student at MIT. So you can see it's also a meter scale device. The VTF had these large orange coils, so it was studying magnetic reconnection in a guide field regime, with the guide field about a factor of 10 stronger than the reconnecting field. So all of these experiments, the system size of the current sheet is 10 centimeters or a few tens of centimeters, magnetic field 100 Gauss, temperatures of order 10 eV, and densities of order 10 to the 12 to 10 to the 14 particles per cubic centimeter. So there's actually a nice recent book chapter that Han-Tao Ji led about laboratory study of collisionless magnetic reconnection that was published recently in Space Science Reviews, where a lot of this research is reviewed. So I'm going to talk first about our experiments to study reconnection with 2D and 3D movable probes. The system size in these experiments, as I mentioned, is pretty small. So our system size compared to the ion gyro radius, or system size compared to the ion skin depth, is only a few. So the two fluid effects are very important here in these experiments. So I'll study and show experiments on the mechanisms of fast reconnection based on two-fluid effects, some experiments on impulsive reconnection and particle acceleration, and then observations of strong Whistler and other types of lower hybrid waves that are naturally driven in the plasma in this case. So this is a schematic of the MRX device, just kind of a cut through it. It's a toroidally symmetric device going around this way, and there's two sets of internal coils, which are given by these gray circles. Those carry current, and when we run the experiment, what we do is either pulse or quickly reduce the current in those coils, and that's what manipulates the magnetic field in the experiment and can drive the plasma into a current sheet. The current sheet is shown as this kind of red region here that's formed. So we actually pull the flux surfaces towards the, what are called the flux cores. And because these plasmas are pretty low temperature, we can put probes directly in it. So there's magnetic and Langmuir probes, which measure density and temperature. And by moving the probes around between shots, we can build up whole profiles of the different plasma quantities. And so yeah, here's an example where you see the current sheet here, and these probes are in there moving around from shot to shot. So all of these experiments also are experiments with a guide field. So there's an additional coil that's creating the guide field. And so one experiment that we did for guide field reconnection is we wanted to understand what balances the very large parallel electric field that's associated with the fast rearrangement of magnetic fields during reconnection. So in particular, if you have a guide field reconnection and you have dBdt, there's a electric field from reconnection, the reconnection electric field, and it's parallel to the magnetic field near the X line. So that's a great challenge to understand how that field can be balanced, because we need to balance that field in order to get the reconnection to happen quickly. So theory prediction, with two-fluid reconnection theory, what tells us that a very important structure is that a quadrupolar density and pressure structure will form near the current sheet. And the effect of this is that when you look parallel along the magnetic field, these pressure gradients contribute to balancing the parallel electric field. And this is a simulation, two-fluid plasma simulation by Adam Stanier. But this idea goes back to the early 90s, and it was actually inspired by trying to understand reconnection in tokamak regimes. So we did this experiment in MRX, and we could see, we produced our current sheet, which is shown here. So this is a measurement of plasma current with a certain value of the guide field, about 70% of the upstream field. And we can directly see that this quadrupolar pressure structure gets developed just as predicted. So we've got a separatrix up here with high pressure, and the opposite one over here with a low pressure, and then the opposite separatrices near the current sheet have a very low pressure condition. And we could also then see quantitatively that this was important by including the pressure term into Ohm's law. So we study a full Ohm's law with a parallel electric field, parallel component of the pressure, and then other terms such as parallel current density, which turns out to be small. So if we take a cut along the current sheet, going from near the X line region then down into the outflow region, we can plot the parallel electric field along this, evaluated from all our plasma measurements, and then also the parallel component of the plasma pressure. And we can see as we get into the outflow region by just about 1 ion skin depth that this term comes up and is balancing it. So this is important confirmation of how pressure terms work during guide field reconnection. So we still actually don't understand what happens very close to the X point. There's some other phenomenon there that has to be balancing the parallel electric field, but we still thought this was a victory. So there's been further work by another postdoc who studied how these structures also then help accelerate the ions down into the outflow region, which I encourage you to take a look at if you're interested. So moving on, I also wanted to show results from experiments at the VTF, so which is another one of these type of experiments. So this is showing, it's another toroidal facility. There are various coils again on the inside, and we're going to pulse current through these coils to manipulate the flux surfaces and drive reconnection. This shows here some magnetic field contours of the in-plane component of the field when we look very close to the current sheet. So you can see there's this current sheet region where the field reverses from one side to the other. This is just a visible light picture of the plasma, and you can see it's kind of brighter there in the current sheet. So in these experiments, we build up the plasma current, and then at some time point we start to drive reconnection and pull current actively into these coils. And what we find in these experiments is the current will build up and form the current sheet and then suddenly release its energy in one burst. And there was a large reconnection electric field that was associated with this. And so yeah, we termed this bursty reconnection. We can see that very strong Whistler and lower hybrid type waves arose and were observed during these events. So here's, again, from a magnetics measurement, we can infer the parallel electric field. And during the reconnection event, where we've got this fast rearrangement of the field, there's a very strong parallel electric field in the current sheet. We had a fast electrostatic probe that could go in and measure fast plasma waves that were propagating in the plasma. And then this just shows some data from that. So at various times, either before the reconnection event, when it's all very quiescent, and then during the reconnection event, there's a large burst of waves, and then it again becomes kind of quiescent again afterwards. If we take the FFT of this, we can see that there's a huge broadband set of waves that gets being driven in the plasma. And it extends all the way from something like the lower hybrid frequency all the way out to the cyclotron frequency. And so for these plasma parameters, the cyclotron frequency was lower than the plasma frequency. So there's like a very strong cutoff effect of the waves at the cyclotron frequency. But we saw this huge broad band of Whistler waves that were generated during the experiment. And so now I thought to include this since there's the nice talk yesterday about all of these other type of various type of radio bursts that are seen in solar probe and other measurements. So I thought it might be interesting to compare these type of observations. We can also see that very strong fast electrons get accelerated during these experiments. So we had a electron energy analyzer sitting in the plasma, and which could observe the tail of the electron population. And during these fast reconnection events, we could see there was a tail population of high energy electrons that got accelerated. The energy was of order like 10 times the thermal energy and carried something about 10% of the total plasma current. If we turn the probe backwards, we didn't see these, so these were clearly getting directed along the field by the reconnection electric field. And so our model also was that these fast electrons drove those Whistler and lower hybrid waves that I showed on the previous slide. And I think this could potentially also be interesting to revisit. I think since these experiments, we've learned a huge amount about how reconnection accelerates particles. So it may be interesting to revisit this and see if this is valuable data for comparing with any of those type of simulations that can be done. Okay, so I'm going to switch gears and talk about these laser plasma experiments now. And the general idea is that laser-driven experiments can access reconnection in a much larger system size regime. This is maybe counterintuitive since the actual laser gets focused down to a pretty small volume, but the magnetic fields are very large and the densities are very high. So in plasma units of like the ion skin depth or the gyro radii, it's a bigger reconnection system. So I'll show the observations from these experiments, including highly extended current sheets and magnetic instabilities, energization of high energy tail populations, and reconnection in relativistic regimes. So overall, I think an important frontier topic, as Hoshino-san was just talking about, is to study reconnection in large systems where there's many interacting flux ropes and plasmoid type structures. First of all, to see if the generation of these structures speeds up the overall reconnection and dissipation of energy. So this is an example simulation that I like from Doughton et al., showing that when you have a reconnection in a larger system, so this is 70 di long current sheet, the reconnection is actually taking place with many interacting flux ropes. So we'd like to see if we can observe this in an experiment as well. Second, as Hoshino-san was just talking about, the particle energization process changes qualitatively when you're in this type of regime, and there's important interaction of these energized particles with the flux ropes. So lasers produce very nice plasmas for plasma astrophysics. When we irradiate a solid with a high power laser, for example, available at NIF or Omega, it can couple 1 to several hundred kilojoules of energy into a small volume, just a few square millimeters in a few nanoseconds. And that creates a plume of very hot plasma, temperatures of order 1 to 10 keV, and densities of order 10 to the 18 or 10 to the 20. The laser propagates all the way to a density called the critical density, which is a fraction of the solid density, but it's still a quite high density by laboratory conditions. And so the corresponding, the ion skin depth is pretty small, and so we can get a regime with large system size compared to the skin depth. Laser experiments have enabled several other types of experiments in the last couple of years. We had experiments on ion Weibel instability, where in this case there was two plasmas that were facing each other and were ablated off. And these plasmas were high enough energy that when they met in the middle, they didn't just stagnate against one another, but actually the ions counterstreamed with one another at the midplane. And that produced a very strongly anisotropic ion distribution, which was strongly unstable to ion Weibel instability, and it produced all of these magnetic filaments that can be seen. So I'll explain this diagnostic a little bit later, but this is a diagnostic sensitive to the magnetic fields. And we can see that when these plasmas interact with each other, it produces all these filamentary magnetic field structure. The other experiment that Derek Schaefer talked about earlier this week was experiments on magnetized collisionless shocks. In this case, we ablate a plasma out into some magnetized ambient plasma, and this strong flow compresses up the magnetic field, and it steepens into a shock, and it lets us start to study shock physics. And so in both of these cases, it's, the fundamental ingredient is that we've got a high energy laser, and that lets us have a large system size. So it lets us observe a shock long enough for it to form and start to evolve, or a Weibel instability where we're going to have many, many filaments in the system. Okay, so laser experiments. So as Hoshino-san was mentioning, these magnetic field in these experiments, one mechanism to produce it is the Biermann battery effect. This is an effect if you have very strong non-equilibrium conditions in a plasma where the density and temperature gradients point in different directions from one another. If this is the case, you can draw a loop in the plasma and see that there's a net EMF around that loop. And as a result, this condition will start to drive a current and produce a magnetic field. And this, in the long pulse laser conditions like I've been mentioning, this produces magnetic fields of order 10 to 50 Tesla. Interestingly, this mechanism is also proposed to provide some of the seed cosmic magnetic fields during the structure formation of galaxies. So there's interesting, astrophysical analogs there too. At the bottom here, I'm showing one of our particle and cell simulations where we're propagating a laser in the simulation and letting it heat up the plasma as it would in the experiment. So we can see our plasma blow off here. Here's the laser energy deposition, and we can see this generation of this Biermann battery magnetic field. So a magnetic reconnection geometry is then formed by having two plumes and letting the two opposing Biermann battery magnetic fields collide with one another. So if we look at in the mid-plane here, where these two plumes are interacting with one another, oppositely directed magnetic fields will be pushed together. So there's a current sheet where there'll be reconnection and magnetic energy dissipation. There have been many experiments on this in the last decade or so. This is an example from Rosenberg et al. I'll explain this type of diagnostic in a moment, but you can see that there's been two plasmas that were born, and that there's an interaction that's happening when these plasmas merge with one another. We've also done particle and cell simulations of this, where, again, like I mentioned, we can do the Biermann battery self-consistently with laser heating of the plasma. So here just is a simulation with two laser spots. It's created two plumes expanding off the target. The blue color is a contour of the magnetic energy, and the green is showing regions of large J.E. So that's magnetic energy dissipation. And so it's occurring in the current sheet here where these plasmas are interacting with each other. And then this is a side-on view showing where the magnetic energy conversion is happening. Just to get oriented a little bit more, we can take a cut from the center of one plume to the other and show some of the quantities. So for example, here's the plasma density cutting between, the plasma magnetic field cutting between the two. So you can see opposite directed magnetic fields from the two plumes has gotten pushed up next to each other. And so there's a strong current that's flowing there. That's the current sheet. And we can also see how the density and the temperature is evolving as this reconnection current sheet is assembled. We've also done a set of simulations just to study the reconnection physics. This was led by Kirill Lezhinin. So we did a series of simulations varying the Lundquist number, like varying the plasma resistivity from low Lundquist number, high resistivity case, up to a high Lundquist number, low resistivity case. And we could see that, so here's a measure of the time for reconnection. So this is, in this case over here, it's a slow reconnection, and it's actually, these two plasmas are just stagnated against one another and not really reconnecting. And then at a critical Lundquist number, the reconnection changes and it becomes a fast reconnection with a formation of a lot of plasmoids. So this shows that there's an opportunity to study different reconnection behavior if we can change the plasma parameters. Finally, there's some very interesting imaging diagnostics that can span from the global to the kinetic scales, so we can observe what's happening in the plasma. Here's an example. There's X-ray emission, which can be processed to get what the plasma temperature is. Here's a set of data. This is the two plumes expanding off the target. And then in the middle here, we can see these plasmas start to interact with one another, and it's getting hot and bright. Some other data we have shows that this is actually getting hot in the current sheet region. There's optical interferometry or refractometry type diagnostics that give us the plasma density. And we can have algorithms now that we can process this to get the plasma density. And then finally, proton radiography, which is sensitive to the magnetic fields. So yeah, we use this one a lot. This is used to measure the electric and magnetic fields in the plasma. The principle is that we have some source of protons and let them stream through the plasma. They're deflected by whatever electric and magnetic fields are there and then imaged on a detector. Okay. And these deflections are proportional to the line integrated Lorentz force on the proton. So the deflection is proportional to the line integrated fields. And it turns out for our usual parameters in these experiments, the magnetic field dominates. We can convert these measurements to the magnetic fields with a few techniques. One is to have some type of mesh and break the protons up into beamlets and map the deflection of the beamlets. And then a second, more powerful way has been developed in the last few years. It's led by Archie, wrote this great paper first on it, and shows how you can directly not have a mesh, but directly solve for how the image that's produced on your detector is consistent with a certain set of magnetic fields. And we've done some work on this as well. And it turns out it's very important to also have the boundary conditions for this reconstruction. So we have an experiment we're measuring the fluence of protons in the middle and then having a mesh on the edge to provide these direct measurements. And we can reconstruct the magnetic field that's producing that. And so here's just an example for a single plume sitting by itself. Okay, so we've done some experiments at the NIF to produce reconnection in very highly extended current sheets. So in these experiments, we've got many beams tiled on a target. These produce the field by the Biermann battery effect, and then have reconnection in the current sheet in the middle. And I'm going to skip this one. And we've been able to analyze and reconstruct the magnetic fields in these experiments. So here's an example proton radiograph from these. These dark regions are from the global, Biermann battery magnetic fields of the two plumes. And then we can also analyze the region where the plasmas are interacting using these reconstruction algorithms. We can infer that we've produced an extremely long but also very thin current sheet. So the current sheet is almost 5 millimeters long, but when we analyze its width, it's only about 25 microns. So this is an extremely large aspect ratio current sheet that's been developed. And the width has gotten very close to the scale of the electron gyro radius or the ion skin depth. Getting such a thin current sheet we think is important because it enables reconnection mechanisms such as the pressure tensor to start to play a role. So we did some estimates based on the Hesse model of pressure tensor, and we could see for these experiments that it would have a very strong magnetic dissipation associated with it. We can come back to this for any questions, but I thought we should just proceed toward the end. We've also done a set of experiments at omega EP with a very high resolution magnetic imaging. In this case, the protons were driven by a short pulse laser interacting with the target. And then we also have a cutout in the target as well so that there's no scattering of the protons. And these experiments, we saw a very interesting set of evolution where we get very large magnetic structures and current fluctuations in the sheet. So we see at early time, the current sheet is barely forming, and then this white interaction region between the two plasmas is growing and extending out. And then by late times, it's also broken up and formed all sorts of structures. We've reconstructed these to produce the plasma current and the upstream magnetic fields. And we can see that there's a very almost laminar current sheet that's formed at early times, almost like the cartoon picture of reconnection. But then at late times, the current sheet is much more highly broken up into many, many current structures that are on various scales. And the current sheet itself is very rippled. Okay, so yeah, so we've actively comparing all of these results to reconnection theory. Finally, we've done some experiments on particle energization. This is very similar geometry, except we've added a particle detector either in the X-line acceleration direction or one of the reconnection outflow directions. We did very careful various kinds of null tests with one beam or the other beam to make sure that these weren't just particles that were accelerated from the laser. And these experiments, in the end, we concluded there was a positive, particle acceleration by this. Interestingly, even with one laser and no reconnection, there's already a tail of high-energy particles just produced by the laser-solid interaction. But when we have two plasmas interact and collide with one another, we can see the tail is energized. Okay. We've done various simulations to see if we can understand this energization. I'm going to move on, though, to one more experiment that was led by one of the illustrious organizers of this workshop that I was minorly involved in, but Louise led this with her grad student, Anthony Raymond. And they did similar experiments, but used the omega EP short pulse lasers, which produced a relativistic plasma. So the plasma temperature itself was of order MeV. In this case, they got a copper K alpha image. So there are the two spots, and they can see, again, a very bright interaction region where these plasmas are forming a current sheet and interacting with one another. And these experiments also observed positive acceleration of the tail particles when you compare non-reconnection and reconnection cases. Okay, so let me summarize here. So these laboratory experiments, I think, are a very exciting platform to study fundamental processes in plasmas relevant to astrophysics. showed our experiments on reconnection and particle acceleration with the laser experiments accessing this new regime with much larger system size, though the beta is larger than 1. So the diagnostic techniques are rapidly improving, and the goal is that these experiments start to strongly constrain our reconnection theories. So there's many opportunities, so please join us or think about how this type of techniques could help you with your own astrophysics problem. So thank you very much.
Let's open the floor for questions. Okay, go ahead.
Thanks for the really nice talk. Could you say a little bit more about the fast electrostatic probe that you used to measure the waves?
So it's a Langmuir probe. So it's, collecting plasma density and it's responsive to both the plasma density and temperature, whatever particle fluxes are coming into it. In this case, though, it was built to be very carefully built to have basically a transmission line all the way from the end all the way out to the scope. So it maintained like a very high bandwidth out to the scope and had basically the full bandwidth of like probably close to 5 or 10 gigahertz of bandwidth to it. So we could see these phenomena in the plasma. And more details. It was also like you also have capacitive coupling to it as well. So it kind of establishes its own bias in the plasma, but then whatever wave comes past feeds through it, and you see it.
Thank you.
Yeah.
Thank you. Okay. Let's see.
Well, in these experiments, when you're colliding two flows that are about to reconnect, the speed of this collision is faster than the alphanic speed, or
the inflow?
Yeah.
Yeah, the inflow it's forming faster than the alphane speed.
So yeah. If you want to test reconnection, there you expect the reconnection speed to be like 0.1 V alphane if it's in the fast regime. So here you're driving faster than the reconnection that you're probing, which is an interesting regime, which is also important in some astrophysical situations. But is there hope to actually probe reconnection specifically that's not forced?
In a slower case?
Yeah. Is there some way to do it slower?
I think, well, so a few things. One is that we would like to see it in the experiment, but from some of our first models of this, of crashing two plasmas together faster than the alphane speed, we saw a lot of like flux pileup, which locally enhanced the alphane speed and helped better reconcile the reconnection rates with what we think with like an alphanic reconnection rate, if you can imagine, right? If we're compressing the plasmas a lot, it was still, it was still way above 0.1, but it wasn't as off the charts as kind of nominally expected. That would be exciting to see. That's one thing we'd like to see in the experiments. I think overall, to get a sub-alphanic inflow would be probably a different experiment design from this, because these the flows are being carried by the plasma ablation, and so it's kind of naturally being born off the target close to the sound speed. So
maybe a follow-up then. Do you see shocks going the other way?
Not conclusively in these observed in these experiments. I mean, I think if we could eventually, if we observe this for a long enough time, we might conclude that there is one there or got the right kind of measurements. Yeah, I think it's possible for it to happen.
Thank you.
Sorry, I was going to ask about shocks, but I have another question. Mm-hmm. Is the phenomenology of the current sheet reproducible? If you have, if you do the same experiment twice, mm-hmm. do you end up with very similar phenomenology as an extent and everything, or are there some turbulence?
We've done various type of repeats of this, and depending what your kind of measurement is, if it's like the length of the current sheet this way, it's fairly reproducible. The fine things are stochastic, but the overall things like the length of the current sheet are are pretty well reproduced. They worked very hard at these facilities to have very reproducible laser power on the target. Like that's, if you want to do fusion, you need to do very well-controlled compression with these lasers. So like the energy balance between them is like very, very precise.
Okay, thank you.
So to discuss a non-thermal particle acceleration, probably you need the size along the electric current. Okay, so my question is in the NIF experiment, how about the size along the three-dimensional size?
Right. So we had an estimate of the reconnection electric field, and we can multiply that by the height of how big we think these could possibly be, just a few millimeters. And that is lower than the acceleration that they're getting. So the acceleration is not just, it's not from an X-line acceleration, it's some other mechanism.
About the first two experiments, the MRX and the one in MIT. Is there a reason why you always have a guide field? Do you always include guide field to the experiments?
No. Well, VTF was built to have a guide field and was required for how the plasma was produced.
Right.
But there's actually a very long history of MRX zero guide field results, which I didn't have time to cover, but they did a whole bunch with observation of Hall magnetic fields, different types of other plasma instabilities in the zero guide field case. So there's a whole long history of that.
Okay.
And then Tom.
Hi, Will. And I think the NIF experiment you've got up there, was that the original idea that you would have a very long current sheet and therefore you were hoping to see plasmoids? And
yeah.
Is there an idea why you didn't see the plasmoids?
Oh, well, hold on. I mean, I'm hoping we'll get there over time, but this is what we've been able to get through in terms of analyzed and everything so far.
Oh,
so
okay, so you think,
don't exclude it yet.
Okay, so you've got other.
This is a fairly early time in the evolution of the plasmas. So yeah, I guess stay tuned. How about that?
Hi, Will. Thanks for a great talk. Lots of interesting results. I have a naive question. You showed some particle energy spectra to show that you had more energization with reconnection.
Yeah.
So how do you know that it is reconnection that is causing that, since you're dumping more energy in? Is there a way to, turn it off?
So what we've done for null experiments was just one laser by itself, the other laser by itself. So just like a plasma plume free to expand on its own. And then you're right that like literally the case where the reconnection, it's really all we can say at this point is it's two plumes crashing into one another. With the particle spectrometer we used also, it has, it's measuring everything that came out and made it to the detector. So it's not at all a localized measurement. I think the way to improve that measurement is to make some type of localized measurement of the particle distribution. And so it may be possible to do that with some type of X-ray measurements to see that it's localized and coming out of a certain volume. I think that's like the right next step for that. Yeah.
Thanks for this nice talk. I just had maybe a very simple question. You were showing us this Lundquist number plot as a function of the reconnection time, or rather the other way around. Yeah. How are you changing the Lundquist number? I'd never seen such high Lundquist number in lab experiments before.
Oh, well, that was a simulation.
Oh, that was simulation.
That was a simulation. Yeah,
okay.
yeah. That was a simulation result. So we had full control over our Lundquist number.
Yes.
And
how high can you go in the lab then?
Oh, we estimated that these so far is of order like 1,000.
1,000.
Yeah.
And is it true that you are seeing like tearing instabilities even kind of onsetting at such low Lundquist numbers? This is always something that I see in the lab experiments that I don't quite understand.
I showed some of these fluctuation results. They don't look like a pure tearing instability.
Okay.
So there's something else involved in them. it seems like the pure tearing instability itself is too slow in these experiments.
Yes.
And there's some other kinetic effects happening to boost it.
Okay.
So yeah, there's other ingredients in there.
And in your beam and field experiments, do you also track the vorticity generation? Because I'm assuming that you should also get strong baroclinicity, exactly where your beam and battery is.
Yeah, so I guess it's
field.
one to one.
Yeah, it should be almost, there's a proportionality constant between the two.
There's no way to directly measure that
Okay.
that I'm aware of.
Okay.
That's grad squared of V, right?
Yeah.
Yeah, that would be a very challenging measurement to make in the lab.
Because you should be generating turbulence and beam and field at the same time in the same spot.
I guess the magnetic field is the easier thing to measure of those two quantities. So
Yes, of course.
we'll take that one.
Okay, thank you.
On the laser experiments or on the lab experiments? The first lab experiments, we had very good measurements of the reconnection rate because you can put magnetic probes straight in there. And so that's MRX and VTF, we could directly measure the reconnection rate. The laser experiments, not precisely now. Very large twiddle in front of it. There's some hope with getting better at these magnetic field reconstructions to measure how the flux is changing with time. So that's kind of our game plan for the next period of time. That would be obviously a very good measurement to make.
All right. Well, with that, let's thank both Will and Professor Hoshino. And, well, let's thank them.